Okay, so the next problem, the next question I'm going to write, and I shall ask each one of you to concentrate on this problem. This is the very important problem, and I am pretty much sure. So once I finish this problem, you are going to understand what I was saying in the next previous session about Taylor's theorem. I was discussing in the previous session, I was discussing Taylor's theorem and its application. Okay, and also I showed you the Maclaurin's version of the Taylor's theorem. Okay, so in this problem, by discussing this problem, I am going to tell you what's happening, and you are going to feel it now, that what is actually happening and what is the utility of Taylor's theorem. This one single problem will help you in this particular regard. And the problem I have selected from the exercise of the note which I have uh, circulated among you. And although I have written it example 2, in the exercise you can find it in section 6.4. Section 6.4 is the exercise, and the problem number 4 I am doing. Problem number 4 I am doing. Okay, so the question is, show that, and you be very attentive while I solve this particular problem. Show that if x greater than 0, x is positive, then 1 plus half x minus 1 by 8 x square, this is less than or equal to root over 1 plus x, less than or equal to 1 plus half x. Very important problem. Okay, so let's try to solve it. Okay, so first of all, you have to guess what the function is, and it is also very important to guess the function correctly. So you can easily say that the function they are talking about is root over 1 plus x. And on the left hand side of this inequality, we have something which is in the form of series, and on the right hand side, which is we have is in the form of a series. So definitely these things, these items on the left hand side and on the right hand side, these are not my desired function. My function is 1 by 1 a square root of 1 plus x. Okay, so we shall start with this. Take fx is equal to under square root 1 plus x. Okay, and we can write it as 1 plus x to the power half. Now we shall try to calculate the derivatives. Okay, that part I'm going to, I was about to, now question is that here one question may come to your mind, that Taylor's series, in the Taylor series, I actually take up to nth derivative, and then n plus 1 derivative is taken of the function. So how many items we must take into consideration to solve this inequality? When we start taking the derivatives of the given function, that how many items we must we take, that will be easily identified. So let's start taking the derivative, and then we'll get to know how many, up to how many terms we must consider. So we have f dash x, this is half 1 plus x to the power half minus 1, and which is half 1 plus x to the power minus half. Okay, so that is your f dash x. Then f double dash x would be half minus half 1 plus x to the power minus half minus 1, which is minus 1 by 4, 1 plus x to the power minus 3 by 2. And f triple dash x will be minus 1 by 4 minus 3 by 2, 1 plus x to the power minus 3 by 2 minus 1, which is 3 by 8, 1 plus x to the power minus 5 by 2. Now you see that if you look at these particular terms, you will see that by putting some values, uh, half x type of terms will can come from this f dash x, and minus 1 by 4 is there, and in this next term we have x squared by 2 factorial type of thing. So from there we can get minus 1 by 8 type of items. Okay, so it is a kind of field that probably up to this we have to consider and not that for the time being. If I consider this point, this function, this point, this point, these three items are considered, then the series will come as it is desired. So let's see what is whether it comes or not. If it doesn't come, then we can take further derivatives if required. Okay, so our next job is to write that now we know Mclaurin series is given as, let us write the series once more. Fx is equal to f of 0, sorry, what was the series? Fx equal to 1 plus x into f dash 0 plus x now let us actually write the form of the series, the form as it was given in the formula. Then I will substitute the values. So we have f of 0 plus x into f dash 0 plus x square by 2 factorial f double dash 0 plus dot 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 plus x to the power n by n factorial f n 0 plus x to the power n plus 1 by n plus 1 factorial f n plus 1 theta x. That is my formula of the, and now I'm going to substitute the values over here. So fx is given as this 1 under square root 1 plus x. So here I'm going to put x equal to 0 over here. Okay, so my x0 becomes 1. Then we write x, and in here I'm going to put in place of x, so I'm going to put 0. So f dash 0 becomes, it would be nice if I write over here, f0 is 1 plus 0, which is 1. F dash 0 will be 1 plus 0, that is 1 to the power minus half, that will be half only. And f double dash 0, that would be minus 1 by 4. 1 plus 0 to the power minus 3 by 2, that minus 1 by 4. Let us put up to this. Okay, so we get x into half, and then we are going to write x square by 2 factorial. F double dash 0 can be written minus 1 by 4, and and the term which we shall denote by r2x. We shall denote by r2x. Now this is the polynomial. You can call this as a polynomial p2x, and the remainder term we are denoting by r2x. Remember, we have considered here n equal to 2, and try to recall what was the formula what the formula you have written when I wrote Taylor's theorem initially. And the remainder term, let me write the formula once again. In the formula, Rn was given as fn plus 1 c by n plus 1 factorial. Okay, and x to the power n plus 1. That was the formula which we wrote actually. That is the Lagrange's form of the remainder. Now here I am writing n, and here I am writing n plus 1. So in case of this, that would be R2. R2, this is actually Rnx. You can call it as Rnx. So my R2x will be F3, the third derivative, F3 C by 2 plus 1, that is 3 factorial x cube. Okay, or if you don't like to write F3, then you can write F double dash triple dash C by 3 factorial x cube. Okay, so you have got your R2. Now our job is to show, if I can show that R2x is positive, then my job is done. Okay, and you see that it would be nice if I write one more term over here. So if I write, let us write it in the way 1 plus half x minus 1 by 8 x square plus R2x. So actually we have got an expression like this. So by calculating that, we have come to know that we have to take, for this particular example, we have to take n equals to 2 to find the to find this inequality. I am trying to find this inequality first of all. Actually, the problem has two parts. First of all, I will try to find this inequality, and then I shall try to find that inequality. Okay. So let us go to the next page. Can I go to the next page? Can I go to the next page? Okay. So we know that C is a point lying between 0 and x. Why is it so? Because in the definition we wrote that C is a point lying between x naught and x. And here my x naught is 0. Also, C is positive and 1 is also positive, a positive number. Therefore, I am going to apply a bit of inequalities which are often used in real number theory. So C is positive, 1 is positive. So we can, from there, it is obvious that 1 plus C is also positive. See, if 1 plus C is positive, then this implies 1 by 1 plus C is also positive. If 2 is positive, then half is also positive. Okay, and if it is so, this implies 1 by 1 plus C to the power 5 by 2, that is also positive. Okay, and this implies 1 plus C to the power minus 5 by 2, that is also positive. And this implies 3 by 8, 1 plus C to the power minus 5 by 2, also positive. And x cubed by 3 factorial, x cubed by 3 factorial, x cubed by 3 factorial, 3 by 8, 1 plus C to the power minus 5 by 2 is also positive, since in the question it is given that x is positive. Otherwise it will not come. Okay, so since if this condition is not given, if x is not positive, then that the product can be negative also. Since x is positive, it is given in the question. So all these items which I have written over here are positive. And if you carefully observe, that is your R2x. So your R2x is positive. Now I'm writing over here. Now what did we get in the previous page? We got this, that your 1 plus x under square root sign, that is equal to 1 plus half x minus 1 by 8 x square plus R2x. So from there I can write R2x as 1 plus x under square root minus 1 plus half x minus 1 by 8 x square. Okay, since r2x is positive, since r2x is positive, so this implies 1 plus x minus 1 plus half x minus 1 by 8 x square is positive, and this implies 1 plus x under square root is greater than 1 plus half x minus 1 by 8 x square. Okay, and for x equal to 0, and as for x equal to 0, the equality holds, the equality holds, then from there we can conclude that 1 plus x is actually greater than or equal to 1 plus half x minus 1 by 8 x square. That is your inequality number 1. That is your inequality number 1. So I'm waiting for 1 minute so that you can copy this particular part of the problem. Then I'm going to move on to the next page to show you the other side of the inequality. And remember, in the Taylor's theorem, if I do not consider the, what did we have? We, in the Taylor's theorem, we wrote fx in terms of fx naught, f dash x naught, and so on. And a big expression came. And lastly, we wrote r and x. Okay, the first expression before r and x, you can call it as p and x. So fx is actually being approximated by a polynomial p and x. Function fx is being approximated by a polynomial p and x with a remainder term r and x present over here. Okay, so this particular result is very important in numerical analysis. In numerical analysis, this particular part is discussed many a times. Okay, even if in the note you can come across a few numerical analysis methods, like Newton's method is there. Okay, Newton's approximation method is there. Newton's root finding method is there. So actually the fx 1 plus x under square root, this root over 1 plus x is not a polynomial. Okay, so I am trying to approximate 1 plus x under square root by a polynomial. So what am I doing by Taylor's theorem? I am trying to approximate the any given function by a polynomial function. Okay, so with your permission, I'm going to the next page to show you the next side of the other side of the inequality. So again, proceeding in a similar manner, and you see, if I want to show this side of the inequality, we have only this part, 1 plus half x. The next part is not shown. So this gives me a hint. This gives me a hint that we must take by taking n equals to 1, we get 1 plus x under square root, that is equal to 1 plus half x plus x square by 2 factorial f double dash c. Okay, and this part you can call as p1x, and this part you can call as r1x. Okay, so now we are interested on r1x. So here r1x is equal to x square by 2 factorial minus 1 by 4. We have already calculated it in the previous page. 1 plus x to the power minus 3 by 2. That is your r1x. And again, we are going to, or and you can write further as x square by uh, 2 factorial. Okay, okay, let us keep up. You can keep it in this manner, or you can write it as x square by 8 minus x square by 8 1 plus x to the power minus 3 by 2. You can write it in this manner also. And one thing that if you write it, so r1x is actually this thing. So we are going to put the value over here. That would be the value will be put at x equal to c, because you see, you don't put x equal to c in this particular part, because this is separate. X square by 2 factorial, it's separate. I'm only I'm taking the derivative of the function, and from in there, in the expression of x, I'm putting x equal to c. So you can write this as minus x square by 8 1 plus c to the power minus 3 by 2. Okay, so that is my r1x. So again, let us proceed in a similar manner. Again, we have, since c is greater than 0, so 1 plus c is greater than 0. This implies 1 plus c to the power minus 3 by 2, as before, is also greater than 0. And this gives you x squared by 8 1 plus c to the power minus 3 by 2 is greater than 0, since x is greater than 0 as given in the question. And this implies minus x squared by 8 1 plus c to the power minus 3 by 2 is less than 0. This implies r1x is less than 0. So we get, therefore, we get r1x less than 0, which implies 1 plus x under square root minus 1 plus half x is less than 0. And this implies 1 plus x under square root is less than 1 plus half x. The equality will hold. The equality will hold for x equal to 0, and so 1 plus x under square root is less than or equal to 1 plus half x. This is my 2. Okay, so I'm waiting one minute for you. So you just copy it, then I'm going to move on to the next page. Okay, so now you see, in the previous page we have shown that this inequality has been shown. 1 plus root under square root 1 plus x is this greater than this, and from 2 we have got this. So combining 1 and 2, combining 1 and 2, we get, combining 1 and 2, we get 1 plus x under square root is a number which lies between 1 plus half x minus 1 by 8 x square and 1 plus half x. Okay, so calculating calculating 1 plus root x under square root may be difficult, but calculating the left hand limit and the right hand limit is not at all difficult. And since we have proved this result, so now see what will happen. if you look at the problem number 5, section 6.4 of my note, problem number 5, okay, this part, they have asked you to approximate two items, 1.2 under square root and root 2. These two items where they have asked you to approximate. So let us talk about, since we are familiar with root 2, let us talk about that. Now, in those days, the mathematicians were so puzzled about these irrational numbers. Previously, when if you go with the development of the number system, so we started with the numbers which God created, the natural numbers, and gradually during the process they have come across, they have generalized their number systems to integers, then rational numbers, and after rational numbers, for some time they stopped, and they thought that rational number set is the complete set of numbers. But suddenly there are some histories that suddenly they have come across numbers like root 2, root 3, etc., pi, where they have seen that the definition of the rational number is not fitting at all. So therefore they have come to know that this number root 2 is actually not this rational number, but it's something else, and they called this type of numbers as irrational numbers. And they proved many results, and ultimately they developed this real number system. And this real number system on which we are working, everything is settled on this real number system, and real number system is the complete ordered field. Okay, a real number system is a complete, it is a complete set, it's an ordered set, because if you take two real numbers, you can say that one real number is greater than another, or they are equal, or the vice versa, whatever. And it is a field, and you know very well what do we mean by field, because now as you have come across vector space, so real number system is a complete ordered field. Okay, but they didn't uh, have any idea about how to calculate root 2. How to calculate root 2? What is the value of root 2? The value which I am now getting, we are now getting uh, using the calculator, and we are in the books we have found that root 2 is this having this value. But in those days, you put yourself, you take yourself, you rewind yourself to primitive stage, and you think that, yeah, this number root 2, what is the value of that? And we do not have any technology, nothing we can do. So how can we guess the value of root 2? Think about this situation. Okay, at this point they tried to approximate the function. They have designed this function 1 plus x under square root and tried to approximate this function with the help of polynomials. Now you see what is happening. To approximate right now it may seem to you very quite obvious, but that point of time it was not obvious. Sometimes we also use periodic drama, isn't it? Periodic drama in movies. So we have to take our mindset to that, otherwise we shall not enjoy Jodha Akbar and etc etc. Okay, so it's kind of that thing. So to approximate root 2, we take, and let us name this inequality as star. We take x equal to 2, x equal to 1, and from star we get the following: 1 plus half 1 minus 1 1 by 8 1 square less than or equal to 1 plus 1 less than or equal to 1 plus half into 1. And you see, this is 1 plus half minus 1 by 8 less than or equal to root 2 less than or equal to 1 plus half means 3 by 2 and this would be 8 plus 4 minus 1 less than or equal to root 2 less than or equal to 3 by 2, and this would be 3 by 2, and 11 by 8 is how much? 11 by 8, you can you can, okay, since we are doing we do not have a calculator, so we can divide. So it is okay. So we are getting 1.37 less than or equal to root 2 less than or equal to 1.5. So you see, so you see, um, at least I can say, I do not know what is root 2, but at least I can say that root 2 is a kind of a number which lies between two numbers. If you do further, you will get like this. So we can put, so you see, root 2 is a number which lies between two numbers 1.375 and 1.5. At least we can say this from this particular analysis. And also probably we have seen a very beautiful thing, that we have come across this statement many a times, but you haven't felt it. Between two rationals, there is an irrational number. You have come across this statement many a times, and between two rationals there is an irrational number, and therefore the set of real number is dense. Okay, so you see 1.375 is a terminating decimal, 1.5 is a terminating decimal. So this is a rational number, this is a rational number, and between these two rational number, an irrational number is existing. Okay, so probably I'm able to I'm able to show you what is the utility and powerfulness of this Taylor theorem. So similarly, if you want to approximate 1.2, similarly, if you want to approximate 1.2, then you select x equal to 0.2. Okay, and from star we get 1 plus half into 0.2 minus 1 by 8.2 whole square less than or equal to 1 plus 0.2 less than or equal to 1 plus half 0.2. Now I shall recommend not to use calculator to calculate these two items, because you do not have the calculator, you are in the primitive stage. Try to guess what will be these values and what will be the rational numbers over here. Okay, so anyways, you can do anything. This 1.2, this maybe, I don't know whether it is a rational number or rational number. Can you say? I don't know. So this number, you see, it's kind of we know that root 2 is a rational number, but see, we cannot say anything about 1.2 under square root over 1.2, whether it is rational or irrational. So at least we can say that, yeah, this number, this particular number will have some value lying between certain values coming from that and certain values coming from that. So we are going to. So do not try to do it manually. Do not use your calculator. Then you can feel it that yeah, it's happening. In the similar manner, you can. There is one another problem in the in 7, exercise 7, section 6.4, exercise 7. I am just writing the problem. You try it by yourself. If x greater than 0, you try after the class, because this is the last session of today's class. After that, whenever you find time, you try to do this problem. If x greater than 0, modulus of 1 plus x to the power 1/3 minus 1 plus 1/3 x minus 1 upon 9 x square mod, this is less than or equal to 5 by 81 x cube. Use this inequality, to approximate cube root of 1.2 and cube root of 2. Do not use calculator. Okay, so you will, if you can show this problem, then if you can find it out, then you will feel that yeah, what is happening, why this Taylor's theorem is important. Otherwise you will not be able to identify just looking at the theorem, and by looking at Mclaurin series. And the first problem which I have done was just a technical problem. It didn't make us learn anything. But this problem is a problem, and the problem which I have given you is a problem which will try to make you learn something, why Taylor's theorem is so important. Okay, so with this I'm going to conclude my today's session. You write your roll numbers quickly in the chat box so that I can save it, and after this class ends you don't have to join again. So we shall meet in the next class. And meanwhile, I am the previous class which I took with CSE section A, the class on this solving system of equations, I have already posted in the YouTube, so you can go through that. Probably you are going through that, I know, because the next examination which will happen, CA2, will be based upon module 2 and module 3, both of that. So accordingly you prepare yourself. Okay, so I'm going to conclude my today's session. Probably everybody, next page. Okay, next page you want to see question again. Okay, just a minute. See, you can get this question. I will tell you about the exam. I will tell you later on. I have not yet decided, and you just prepare yourself. And you can, if you are missing something, you can get this. I have shared the note of this in the Google Classroom already, so you can get the question from there. This is the reference number, example 7. You just look at this particular problem. From there you can get it. Try to do it. Okay, you'll enjoy. Okay, can I leave? Okay, nobody is responding, then probably this is a kind of nod. Bye for now.